Okay, so now let's talk about category theory, but just like in a really wide area. Okay, like I want to give you the view of category theory as far as I was able to look into it. Okay, because we now have these basic parts of category theory: categories, functors, and natural transformations. So we can now just like see how these things can be generalized, how far people can go with this stuff. Okay, so this will be like outside of programming. It will be real math, deep math. Okay, so we are diving into this deep math. So, well, first of all, let's start with a simple thing, okay? Natural transformations. There are mappings of functors, right? Now, every time we have mappings of things, right, we ask ourselves a question, right? Just like, well, first of all, do these mappings compose? Huh? So every time you think about mappings, that should be the first thing that comes to your mind. Do they compose? Can we compose natural transformations? Okay, what would it mean to compose two natural transformations? So we would have one natural transformation alpha between functors f and g, right? And we would have another transformation, let's say beta, between functors from g to some h, right? So let me draw the picture here. So we have two categories, right? So we fixed two categories, and now we have three functors, f, g, and h, right? So under this functor f, well, let's pick an element here, right? So under this functor f, a will go into fa, right? Under the functor, so this is functor f, this is functor g. So we have ga, and we have a functor, and we have h, functor h, so we have ha, right? So one natural transformation is this family of morphisms, and this is the component at A, right? So we have alpha A, and the natural transformation between G and H would give us a component, let's say, beta at A, right? So, obviously, right, these are two morphisms. They compose. This is a category, after all, right? So if they compose, then hey, there is this morphism here, and let's call it, I don't know, should we call it gamma, or should we call it just beta after alpha? Okay, I'm going to use a little dot, not a circle in this case. So, is this a natural transformation? Well, not immediately, because we have to check one thing, right? The thing that we have to check is whether it's natural, really, right? Naturality condition. So we would want to have, okay, so we would have to add another point, another object B, right? And this object B, okay, how do we draw this? Okay, so we have FB, we have GB, and I always end up with a category that's too small, you know? Small categories. So maybe I shouldn't be just, drawing these circles and HB, right? So first of all, we have natural transformation alpha B. Here we have beta B, right? And of course, the candidate for our composition is this one. That's the beta after alpha at B. This is at A, and this is at B, right? And now we have these morphisms that are lifted by the functors. So this is FF, this is GF, and this is HF, right? Yeah? So that's a lot of arrows, but it's pretty straightforward, right? I mean, I'm just like repeating the same square twice. So naturality condition for each of them says, this way is the same as this way. And here, this way is the same as this way. Now what we want to show is that this way is the same as this way. Right? That would be our naturality square. But this big square is actually a composition of these two small squares. So like, instead of going this way and this, I can go, instead of going this way, I can go this way and then turn here and then here, right? And by naturality it's the same. But instead of going this way, I can turn here and go this way by naturality of this square, and then down here, right? This is called diagram chasing. Okay, it has a name. It actually is called diagram chasing, and it's a very simple thing, It's like you just have to point your finger at. But when you are writing like a paper or a book, you have to write down, here you have to go this way, and this way. Or sometimes people say, simple diagram chasing shows that this is true.
Left as an exercise to the reader.
Yes, exactly. Okay. So we have composition. Okay. So what's the next question? If we can compose natural transformations, is there an identity? Identity natural transformation. So identity natural transformation would be a transformation from F to F, right? So, F turns this A into FA, right? So we would have to have a component at A would be really a little thing that goes back to FA, right? So this would be our identity at A. And of course it has to compose with any other natural transformation to give back this other natural transformation. So the only way to do this is if this morphism here is really an identity, right? So an identity natural transformation is just this family of identity morphisms from FA to FA, right? So for any functor F, we can build this identity morphism. So what's the next question? They compose, and there's an identity. Is the composition associative, right? Well, kind of obviously it is, right? Because In components, it's associative, because in components, it's just a composition of morphisms. In composition of morphisms, it's associative, right? And why were we asking these questions? Because?
The category, right?
Because of category, right? So, okay, so what category are we talking about? What are the objects? Functors. Okay. So functors,
Makes sense.
functors between two categories, C and D, they form a category in which these functors are objects and natural transformations are morphisms. Okay? So we have just lifted ourselves to a completely new level of abstraction where functors that were morphisms between categories suddenly now become objects in a category, and morphisms between them are natural transformations. Okay? So this is the notation that people use for a functor category. Between two categories C and D, a functor category, they put these square brackets, or sometimes they use this notation, d to the power of c. Okay, that kind of suggests something, right? Okay. So we have a category of functors between any two categories, right? But we also talked about this category of categories, cat, right? So let's go back to this. So we have cat, and in cat, objects are categories. So we have the category C and the category D inside cat, okay? I'll draw the big cat, right? Now morphisms in cat, remember, were functors. This is like functor F, functor G. Okay? But now we have morphisms between functors. So how do we draw this? Okay, let's draw it like this. Now we have a much more interesting structure. We have a category that has objects, morphisms between objects, and morphisms between morphisms. Okay? So these are called, sometimes this is called one morphism and this is called a two morphism in this picture. Or you might also see people calling this cells. So this would be a one cell and this would be a two cell. And sometimes they even say 0 cells are objects, 1 cells are morphisms between objects, 2 cells are morphisms between morphisms, or between 1 cells. Okay? And this kind of structure, like this, is called a two category. So a category of categories has more structure. It's actually a two category. Right? Now, let's think about the home set in this category, right? A home set between two categories, C and D, that's a set of functors, right? A set of functors between two categories is a home set in cat. Okay, I'm saying set because I'm thinking small, right? I'm thinking small category. A small category is a category in which we have a set of objects, right? Objects form a set. So cat is usually thought of as a category of small categories, right? And functors between small categories also form a set. So a category in which morphisms form a set is called a locally small category. Locally small means Hom sets are sets. Now, of course, this is like crazy talk because Hom sets are sets, right? So what else can there be, right? Well, but here, look at this. A Hom set between these two categories actually is a category, right? It's a category. It's a category in this category F CD, right? It's a functor category. So a Hom set in cat is not only a set, but it's also a category. And being a category, wait a moment, being a category, it's also an element of cat, right? So C, comma D is an element in cat. Okay, but we also had this, so this is very similar to what we had in set, right? In set we had that the Hom set is also an element of set, right? But treated as a set. Here we have a Hom set that's a category, and it's an element of the same category, right? So this is a little bit one step up from what we saw in set, right? But still, but the thing that we did in other categories was to also try to like encapsulate a Hom set as an object in a category, but we did this using exponential objects, right? So if inside cat we try to build an exponential object that corresponds to this Hom set, right? Then it would be called d to the power of c, right? So can we actually do this? I mean, how did we construct an exponential object? We constructed it because we had product, right? We had to start with a product. It was a universal construction that starts with a product. Now, do we have a product in cat?
That looks like a product. It's got square brackets instead of brackets.
Well, no, we actually had a product in cat. Remember product category? There was this very simple construction. You take two categories and you form pairs of objects, right? That's a product category. So a product category is actually a good product in cat, right? Just like in set, we constructed, you know, the product in set we constructed as pairs of elements, right? But then we also said, okay, but another way of doing this is using universal construction. We construct a product. And these two products were identical, you know? Maybe I didn't show that, but I should have shown that, right? That actually both definitions give you the same thing. That the definition of product as pairs of elements and categorical product with these projections and, you know, that actually gives the same thing. So the same is true here. This category of functor category CD is the same as d to the power of c. You know? So we start with a product category, c cross d, and then do the universal construction, and we get the exponential object. So in fact, cat is sort of like Cartesian closed category. Okay, so like everything connects to everything here, right? That's a cool thing. But then, you know, once you see this, then the next question is, okay, so is this a normal thing? Is this just like one special example of a category in which a home set is actually an object from a category? And the answer is, well, how about defining a category in which instead of home sets, you have home objects? So you build a category, because this whole thing with sets, right? We don't like sets, really. It's like we build category theory to kind of get away from sets, right? And yet we are stuck with home sets, which are sets. What if we wanted to get away from sets and then say, okay, so can we build a category in which instead of home sets we have home objects? And turns out, yes, you can do that. These home objects have to be from a special category. I mean, it has to be a monoidal category, right? Because you have to have like a multiplication in this category, because you want to be able to build, you know, composition using home sets. So building composition using home set rather than elements of home sets, because we define composition using elements of home sets, the morphisms, right? This morphism, and so on. Now, if you don't have elements, because you have an object in a category, you cannot talk about elements, then you have to like take a, you know, a product of two such objects and define composition in bulk, which is possible, okay? I'm not going into details of it. They are not that complicated, actually. But you can build a category in which, instead of home sets, you have home objects, and it's called an enriched category. So there's a whole theory of enriched categories. Enriched category is a category in which these guys are objects from some other category, from a monoidal category. Here, these home objects are actually objects in the same category, right? But it, in general, doesn't have to be like this. Now, this is still, you know, so I said this was a two category, right? A two category would be a category in which you have one cells and two cells, right? But you have two compositions here, right? You have a composition of let me change names here. So you have a composition of morphisms, or in this case, functors. So you can compose F with G, so C, D, E. Right? And you have the composition of natural transformation. So this is alpha, and this is beta, right? You can compose alpha with beta. So this is F, F prime, F double prime, okay? This is why this composition that I talked about is called a vertical composition. Because in this picture it goes vertically, okay? So you have vertical composition of natural transformations. That's the composition I define. You also have composition of functors going this way, right? How do these work together? So if you have composition of functors here, you can compose these two functors. So this is G after F, right? Let me get rid of this guy first. Okay. So we have G and G prime. And let's say this is beta. Now look what I can do. I can compose G prime after F prime to get this guy. G prime after F prime. Okay? Now, is there a natural transformation between G after F and G prime after F prime? Can we construct it? We would have to do this in components, right? So we'll just, we would pick a component here, let's say some A, right? And then under F, it would go into FA. Under G, it would into GA, right? So FA, GA. Now alpha would be this guy, alpha A, right? But now I have, so this is under F,
F prime.
F prime, sorry, F prime, right? But now I have further split. So I can go G on this or G prime. And I can go G and G prime on this guy as well, right? So this is G after F on A, right? This is G prime after F on A. This is G after F prime on A. And this is G prime after F prime on A. Okay? So I have this bunch of things, right? Now, moreover, this is not the end, right? Alpha A is a morphism here. So this morphism can be transported or lifted by G. Okay, so if I lift it by G, it should go between GFA and GF prime, right? Right, okay. So this is G lifting alpha A, okay? Oh, G lifting alpha A. This is visible, okay? And this guy, of course, will be G prime lifting alpha A, right? Are you chasing this diagram? Okay. And now where's beta?
Beta goes between G and G prime in both cases.
Between G and G prime, right? So I should use a different color here, huh? So this is my beta, and this is my beta. Right? Oh, okay. So finally, the composition would go from GF to G prime F prime, right? I want this new big transformation from GF to G prime F prime, from GF to G prime F prime. Okay, that just cuts right through this, right? But there are two ways of getting to this place, right? One is through here, and one is through here. Which one should I pick? They are the same, right? because this is a naturality square. Okay? So, this works, okay? And as an exercise, okay, you have to have another point B, right? And another morphism here. And show naturality condition for this guy. This is really fun. This is an exercise for the reader, okay? For a dedicated reader. I think this is what McLean said in his book. It's an exercise for a dedicated reader. Because you really have to be dedicated to chase this diagram. Because you have to like have 2 copies of this diagram and chase all these arrows around. But it's just chasing arrows. It's you know, there's nothing much to it. It's just that it's a huge diagram and lots of arrows. So this is called horizontal composition of alpha and beta. And this is actually beta circle alpha. At least this is what McLean calls it, beta circle alpha. As opposed to the vertical composition, which was beta dot alpha, right? And now, since we love this diagram chasing so much, you know, the next thing to chase is actually, what if you have, you know, beta and beta prime, and here you have alpha and alpha prime, right? There is a combination of these called the interchange law, in which you say that if I first vertically compose these and vertically compose these, and then I horizontally compose, then it's the same as if I first vertically compose and then horizontally compose. Okay? I'm not going to write it down, but that's called an interchange law. So, real definition of a 2-category involves both vertical composition and horizontal composition of 2 cells, right? And the interchange law. Okay? So this is what people do. Okay. Is this complicated enough? Or no, right? Because the next thing to do, okay, and this will not be on the test, so don't worry. The next thing is this interesting thought that if you have morphisms between morphisms, then you can also have isomorphisms between morphisms, right? So if you have isomorphisms between morphisms, then maybe you know, like, first of all, we said we don't like sets, right? Being category theorists, we don't like sets too much. Second thing we don't like is equality, right? And like all these laws that we were talking about, these commuting diagrams, they always involved equality of morphisms, right? Like if you compose these 2 morphisms, you get exactly the same morphisms as if you compose these 2 other morphisms, right? So these were all equalities of morphisms. And because home sets were sets, equality made sense because it's just equality of elements in a set. But in general, you know, we don't like equality, we don't like sets, and we don't like equality. And if we are going outside of sets, like in enriched categories, then we are also going outside of equality of elements. Okay? So, how about if we say, let's forget about equality and just say all these laws in which we use commuting diagrams, let's just say they are up to isomorphism. Because now we have isomorphisms between morphisms, right? We have these two cells, which are morphisms between morphisms. And if they are invertible, then we have isomorphisms between morphisms, right? So what if we define a category in which things are defined up to isomorphism? So we start with a two category, like this, right? But we say, well, so what are the basic laws of every category? Associativity and identity, right? What if we say associativity is up to an isomorphism, and so with identity? So like if you associate one way and associate the other way, then they are not equal, but there is a morphism between them, right? This morphism, let's call it an associator, okay? Right. And same with identity, you know, left identity, right identity, left ident. What is it called? Identitor? No, I don't know what it's called. Right? So if we start defining the stuff up to isomorphism, then suddenly from a two category, we are getting into something called a bicategory. Subtle distinction between two category and bicategory. In a bicategory, categorical laws are up to isomorphism. Okay? And actually there are examples of categories that are bicategories. That it's not enough, you know, they are loose enough so that they form a bicategory rather than a two category. They are lax. I mean, mathematicians call it lax when something is not really equal, but up to an isomorphism, that's a lax thing, okay, or relaxed. So these laws are relaxed. Now the problem with this stuff is, and this is all great and people work on this, right? Why haven't they finished working on this? Because once you have a lax category, or you have a bicategory, then there is something called coherence laws, right? Like if things are not exactly equal but up to an isomorphism, then you have more things that you have to like show that it's the same thing, because there are different ways of chasing diagrams now, because you are chasing a diagram this way and then you have to chase it through this associator, for instance, right? So now you have to have laws for these associators and for these identifiers, right? So these are coherence laws. And it turns out that these coherence laws, maybe in the case of bicategory, they are not that complicated. I think Saunders MacLean had some, you know, showed that like just a few diagrams, like a pentagon diagram and stuff like this, you know, and that showed that that's all the coherence that you want. But of course, once you have a two category, what stops you from creating a three category, four category, five category, right? Well, it turns out that if you go up this way, at every level, you get lots of coherence laws, okay? And moreover, you can pick different ones. So it's not unique. And this is like really screwing up the higher order categories. Okay? So, there is another group of people who say, let's forget about n categories. Okay? There are these n category people, right? There are people who say, the problem with this stuff is that these morphisms are not invertible. Okay? What if we have a category in which all morphisms are invertible? And I think I mentioned it before, that a category in which morphisms are invertible is called a groupoid. Okay? So if you start doing the same thing with groupoids instead of categories, turned out that you can have like n groupoids. And coherence laws are simple for groupoids. Okay? So they say, the groupoid people now say to n category people, you know, that's wrong direction. You know, the correct thing to do is work with groupoids. Okay? And in particular, if you go with n high enough, you know, at some point you say, well, what's wrong with infinity? Infinity groupoids. Okay? An infinity groupoid would be something that has 0 cells, objects, right? 1 cells, morphisms between them. 2 cells between morphisms. 3 cells between morphisms of morphisms. 4 cells, and so on to infinity and beyond. Right? And it turns out that this is exactly the structure of the famous homotopy type theory. Okay? So homotopy type theorists are the people who say groupoids are the way to go, not n categories. We know how to do groupoids, and they make sense. And n categories don't make sense. Okay? So this is where these things are right now. I think that's like the overview of category theory and homotopy type theory. Very shallow, but wide. Okay? All right. I think that will be enough for today. Thank you.